Hello, Math 1224. This is Dr. P with Lesson Launch 23.1, Mystery Models. So as you can see here, I have put up the setup for the rabbit problem that we did in class. This idea that at any given time, the rate of population increase is 0.3 times the population size. This is the model that we worked with in class. Now, when you develop this model into a population function, you were using something like Euler's method. You were starting with some initial population size, which I think I gave you p of 0 equals 2,000 or something like that. I think it was 2,000. And then you stepped forward by a year or by a half a year or by some regular increment and figured out what the population would be at future times. So now I want to talk about how we actually solve this type of problem quickly in practice. Because we actually don't solve it using Euler's method. Euler's method is actually very nice and versatile and can be used on a lot of differential equations that can't easily be solved by hand. But this, as you've probably figured out, actually does lead to a differential equation that can be solved by hand. That differential equation is dp dt, that is the rate of change of the population, is equal to 0.3 times p. Okay, which means this looks an awful lot like the differential equation that Driscia showed us how to solve when we were just getting started with this stuff. So let's see how to solve this using the technique that we developed in class last time. So this is separable. We can actually, now that we have Nicole's and Logan's blessing, we can take this dt, we can multiply both sides by it, move it to the other side, and get dp equals 0.3 p dt. And then we can take this p here, divide by p, get it over to this side. So dividing by p on both sides gives me dp over p equals 0.3 t. All right, and then, 0.3 dt. Sorry about that, dt. There we go. And then integrating on both sides gives me, let's see, the integral of dp over p equals the integral of 0.3 dt. And then going ahead and finding the antiderivatives, I get natural log of absolute value of p equals, let's see, I believe it's just 0.3t plus c. Okay, we got to have that constant on at least one side of the equation. Now, in this case, I'm going to make a judgment call here. Normally, I need to have this absolute value of p here, but here I'm talking about population. I'm going to assume that the rabbit population can't ever be negative, and just say that natural log of p, sin absolute value, equals 0.3t plus c. And then we're going to do the same thing that we saw in class. We're going to exponentiate both sides of the equation and get e to the natural log of p. Notice I'm writing this as a separate step, equals e to the 0.3t plus c. And then I'm going to make the same observation that Logan made, which is that we can split that right-hand side up and get e to the 0.3t times e to the c. And e to the c is just another constant. So I'm going to get p equals, p of t equals some constant a times e to the 0.3t. And now I can take that initial information I had, which was that p of 0 was equal to 2,000. That is, the population at time 0 was 2,000 rabbits. And I can use that information in this model to find the value of a. Okay, so I know that p of 0 should be 2,000. 2,000 should be equal to a times e to the 0.3 times 0. So I'm just taking that t, substituting 0 for it in all instances. And that gives me 2,000 equals a times e to the 0. E to the 0, though, is just 1. So that's really just saying that a is 2,000. Okay, so now my model, my population model for rabbits, is going to be p of t equals 2,000 times e to the 0.3t, which I think is the same thing we came up with in class. Now, when we did it in class, we did it using a much more convoluted method, I guess you could say. We did it by taking the compound interest model for rabbits and took the limit as the step size goes to 0. Now, let me just say that this is what we did here is a perfectly valid method for arriving at this population model. We didn't take any illegal shortcuts. The work that we did in class actually was a way of showing that the derivative of the function e to the kt is k times e to the kt. That's actually what that was doing. even though we didn't really highlight that in class. So what we did there had some importance. But, from now on, we're going to solve this differential equation this way. We're not going to do it by taking a limit as n goes to infinity. As much fun as that was, and as much as I'd be delighted to do it again, if anyone ever asked in class for me to do it again. Anyway, we'll see if anyone takes me up on that. Okay, so that's one population model. Now I want to show one more example, just to give an idea of how we deal with a situation where we don't know as much. Because actually, when you think about it, I realize that scenario that I gave you in class about rabbits was artificial in any number of ways. But one way in which it's artificial is, what if we don't know? Because you normally won't know. What if we don't know that parameter 0.3? That is, what if we don't know that the rate of change of the rabbit population is 0.3 times the rabbit population? How would anyone really ever know that in real life? So what if we just instead start with the assumption that unless there are some external conditions like predators or, an environment's carrying capacity, in the absence of all of those factors, we can assume, at least I think we can assume, I'm not a population dynamics expert by any means, but let's assume anyway, that the rate of population growth is proportional to population size at any given time. Let's assume that that's all we know. We don't know that there's a multiplier of 0.3 there. We just know that the rate of growth is proportional to the population size. And this is something that's continuously true. All right, and let's also assume that I have 2 bits of information about my population function. Let's assume again that p of 0 is 2,000. But let's just say that I happen to know by direct observation that p after, let's say 2 years, let's say that we know that's 3,000. Okay, so now this is different from the previous rabbit problem, because I think that the previous one had p of 2 quite a bit greater than 3,000. So we're now changing the scenario a bit. All right, so let's see. So what am I going to need to do to figure out what my population function is? Well, first thing I'm going to do is I'm going to write down some differential equation that I know is true. Okay, and it's going to be a lot more generic this time because I don't know that this is equal to 0.3 times the population size. I just know it's some constant of proportionality times the population. All right, so now that dp dt equals kp. And that k is just going to have to remain a mystery for right now. We're going to have to deal with it being there and solve the differential equation in spite of that being there. All right, so we're going to use the same technique as last time. I'm going to divide both sides by p and multiply both sides by dt and get dp over p equals k times dt. All right, and then integrate both sides. And that's going to give us natural log of absolute value of p equals kt plus c. Now again, I'm going to assume that what I'm working with is a population, and I'm going to drop that absolute value. And note that if you do it, you should always have some reason for it, and I should probably make a habit of documenting that. So p population is always greater than 0. Now don't drop the absolute value unless you absolutely know you can. There's no harm in keeping it around for a bit. But in this case, I don't know, I think it's silly to have around. Population is always greater than 0, so I'm just going to leave that absolute value off. Okay, so I know that the natural log of p is equal to kt plus c. And so I know that e to the natural log p is equal at all times to e to the kt plus c. So again, separating off that right side into 2 separate factors, e to the kt times e to the c, I'm going to get population at time t equal to some constant, a. So let me just put over here, I'm letting a equal e to the c. It's always a good habit to do that, just so that people know what the heck you're doing. Okay, sorry, I'm just trying to clean up my penmanship there. Okay, e to the c. There we go. So p of t is going to equal a times e to the kt. So now look at this. Now I have 2 mystery constants, which that probably puts in a different light the fact that I gave you at the beginning of this problem 2 pieces of information. And you're probably already starting to form an opinion about what each of those pieces of information is going to give us. The fact that P of 0 is 2000, actually that's going to tell me the value of A. Let's find out why. So now I'm going to solve for the unknown parameters. So if I use the fact that P of 0 is 2000, then that's going to give me using this equation here, that's going to give me that 2000 is equal to A times e to the k times 0. Well, e to the k times 0 is just 1, so this means that A is 2000. Okay? So that's the same as before. But now what about the fact that P of 0 is, or sorry, P of 2 is 3000? All right, what's that going to mean? Okay, now I'm starting to fire up my calculator because I have a feeling I'm going to need it here in just a minute. My calculator is actually my laptop. So that means that 3000 is going to equal A, which I now know is 2000, so I can just go ahead and call it 2000. 2000 times e to the k times 2. All right, so now I have a little bit of algebra to do. Let's see, I'm just getting my calculator ready here. Okay, so what does this mean? This means that 3000 over 2000 is equal to e to the 2k. Now I have to think, how do I solve an equation like that? If k is what I'm trying to find, then I will probably make progress by taking the natural log of both sides. Now that left-hand side is just 3/2, so I'll just call it natural log of 3/2 on the left, and that means the right side, if I take the natural log of e to the 2k, I just get 2k. So that means that k is equal to 1/2 natural log of 3/2. And now let me punch that into Cortana here. Sorry, I feel a little bit dirty doing product placement for Windows. 0.5 times natural log of 1.5. That gives me 0.203. So that means that k is 0.203. All right, so that suggests that my correct population model is, with all the parameters filled in, P of t equals 2000 e to the 0.203 t. And you can actually go back and check that first of all, it satisfies the original differential equation, that this satisfies this equation here, dp over dt equals k times p, where k is now 0.203. And you can also check that it satisfies, where were they? Oh yeah, both of these initial conditions here. P of 0 is 2000 and P of 2 is 3000. So this is a situation in which we have, in some sense, two missing parameters, even though there only appears one of them in this differential equation here. The other one comes from the integration. So that is a more generic growth model. If you have two bits of information, you can figure out any exponential growth model, which is something you may have known from high school, but you probably never did it with differential equations. Okay, I was actually going to wrap up there, but I just realized there's one more thing I want to mention about this, one more little insight that we can get out of all this work here, because right now, 2000, that 2000 represents the initial population of rabbits, or whatever it is we're talking about. That's the initial population. That is the population when t is 0. But what does this number mean? What in the world, what insight can I get about 0.203? Well, it turns out that 0.203, well, you may remember in the last problem, we came up with a formula involving an e to the 0.3t. And that was a situation where the rabbit population growth in rabbits per year was 30% of the rabbit population size. So that was like a population growth rate, continuous growth rate of 30% per year. So in this case, in this problem, what this k means is that we're talking about an annual growth rate, annual continuous growth rate, sorry, I'm in the lower corner of my tablet here, of 20.3%, which is kind of nice to know. It's nice to know that we can get there just based on this little bit of information that we were given here. And by the way, if you were to do some standard method that you learned in Calculus 2, like look at the growth rate or the percentage growth from year 0 to year 2, and see you grew by 50%. you could come up with some idea of what the growth rate is, but you wouldn't come up with 20.3%. At least not the method I'm thinking of, because this is a continuous growth rate, and the way that you learned to do this problem in Algebra 2 was using discrete intervals of growth. So anyway, just something I thought you might like to know, and also might be on the test, but that's not why you should want to know it. I don't know, I feel like we should just be curious about these things. Okay, sorry, I'm going off on a tangent now. In the next video, I'll talk, I hope, briefly about decay, so stay tuned.